I think the next order of business is to take this theorem we established in the last video, that the general solution has that form, where these solve the characteristic polynomial. The characteristic polynomial, also called the characteristic equation, looks like this, right? This is the characteristic, I was going to abbreviate it, or equation, polynomial. We called it up there. So that's the general solution if we have distinct roots. Okay? This is when we have the distinct root, two different roots. Okay? Keep that in mind because we're going to solve one. So here we're going to have one here where the C1 is 11 and the C2 is minus 28, like so. And we're going to find the general solution. So the first thing to do with this is write down the characteristic polynomial. And I'm hopeful to see this when you're solving this. It has that form. If you want to scroll back up and see, I guess it's right there in front of us. R2 is C1R plus C2, C1R plus C2. And we need to find the solution, so I'm going to rewrite that as R squared minus 11R plus 28 is equal to 0. And that's factorable. R minus 4, R minus 7 is equal to 0. So R1 is 4, R2 is 7. It doesn't matter which one you call R1 and R2, but the general solution will be alpha times 4 to the n plus beta times 7 to the n for constants alpha and beta. So any choice of constants for alpha and beta will give us a solution there. Sometimes I know I'm going to use alpha 1 and alpha 2 or just alpha and beta. They're just two letters to stand for the arbitrary constants that will give a solution. That's the general solution. And now the next part we're going to say is, can we find the unique solution, the one and only solution of the initial value problem that gives us the same recurrence relation, but we're now given some initial conditions. Since it's order 2, that should be a 2 there. I hope that's what I had before. I did not. That should be a 2 as well. Since it's order 2, we will need 2 initial conditions to pin it down. Okay, so make sure you catch that change I made there. The second one should be a sub n minus 2. I didn't realize I had a typo there. But let's go ahead and see what we have. So we have in general, an is equal alpha 4 to the n plus beta 7 to the n. And now I'm going to impose these conditions. A0 is equal to 3. That's the same thing as saying 3 is equal to alpha times 4 to the 0, because n is 0 here, plus beta times 7 to the 0. So that's just alpha plus beta. What we're going to get is 2 equations and 2 unknowns. The other equation is going to come from alpha 1 is equal to, or a1 is equal to 6. So that's the same thing as saying 6, that's a1, is equal to alpha times 4 to the 1 plus beta times 7 to the 1. And that's 4 alpha plus 7 beta. Okay, so we have alpha plus beta is equal to 3, and 4 alpha plus 7 beta is equal to 6. That's an easy enough thing to solve. You've solved this kind of equation or system of equations before, I'm sure. I, in this case, would do elimination, but you can do substitution. I think I'd take 4 of this times 4 and get 4 alpha plus 4 beta is equal to 12, and subtract that from 4 alpha plus 7 beta is equal to 6. So that would give us, subtracting that would give us 3 beta is equal to minus 6, so beta is minus 2. And having beta minus 2 up here says that alpha is 5. So the solution would be an is equal to 5 times 4 to the n minus 2 times 7 to the n. So that's the unique solution once we impose the initial conditions on that. Okay, so that's how that works out, and that's you'll be given some problems like that to practice on. The second theorem that I'm giving you here will take care of the case where we have a double root for the characteristic polynomial. Remember, the characteristic polynomial would be r squared is equal to c1r plus c2 that we got by substituting r to the n as a potential solution in there, and found out that would work out. So this theorem says the general solution of the second order linear homogeneous constant coefficient recurrence relation, as I've circled here, whose characteristic polynomial, in green below, has a double root r, just a single number that appears as a double root, is, and this is very curious, it catches a lot of people by surprise. I'm going to highlight the one thing that's very different here, and that is this factor of n right there. N, okay? Not a factorial, I'm just emphasizing it. Okay, so it has alpha 1, r to the n, like it did before, but now alpha 2, it's not just r to the n, alpha 2 and r to the n. You might think, wow, where the heck does that come from? I am not going to go into this in great detail, but I will give you an indication of where it's coming from. Again, alpha 1 and alpha 2 are arbitrary constants in this solution. And if you have two initial values, a1 and a0 and a1, then there is a unique solution. But the above in the box is the general solution, all the possible solutions. So where in the world does this n come from? Well, in order for the characteristic equation to have a double root, the characteristic polynomial would have to have the form x minus r squared, like so. So r, particular r, is a double root. Now I'm using x here as the variable, whereas we've used r before, but I wanted to emphasize that this r is the double root of it. So this is the same as x squared is equal to, this equal to 0 is the same as x squared is equal to 2rx minus r squared. And that's what corresponds to the recurrence relation. It would be an is equal to 2r an minus 1 minus r squared an minus 2. That would give us this characteristic polynomial. And if you consider the case, let's try initial conditions a0 is equal to 0 and a1 is equal to r to see what happens. This is the simplest pairing of initial conditions, I think, to see that what happens when you do this is gives you that n as a that n appears. So if we do this and look at a2 would be 2r a0, sorry, a1, which is r, minus r squared times a0, which is 0, and that's 2r squared. There's the 2. A3 would be 2r. I'm looking back up here, of course. And now it's going to be a2. A2 is right above. That's 2r squared, a2. And then it's minus r squared times a1. There's a1 right there, times r. And if you calculate that, that's 4r cubed minus r cubed. It's 3r cubed. All right, well, I'm not going to do any more, but you can check a4 is equal to 4r to the fourth, and so that n is popping out there. Okay, that's the extent to which I'm going to explain that, but that's how the theorem works out, and I don't think I'll go into the proof anymore. In this case, the distinct root case, I think, gives you a flavor of how you would pursue this as well by using a mathematical induction proof, as we'll do in class, for the distinct root case. What I want to do following this is do an example of that, and maybe some other examples, and look at a more general case where we have higher order. So I'll do that in the next video.